Hello, thank you for being here. Today I'm going to talk about, well, forensics and reverse engineering on Android. First, I just introduce a bit myself. I work at the French National Network and Information Security Agency, which you may know with Loïc Duflo's work. That were pretty awesome, and also home of the French CERT. I'm part of the pen testing team, but I also have a bit of spare time where I can do some research. So, the outline of the talk today is pretty easy. I will start with a generic introduction on Android, then go forward with forensics, first memory, and then file system forensics. And of course, we'll go to reverse engineering because forensics sometimes need reverse engineering to help. And a few words to conclude. So I'm not going to give you the talk with no cell phones that are everywhere and everything. And just say a few words on what's Android because it's pretty specific. It's not something that was there before. So it's an operating system that is based on the Linux kernel, but with a few patches mainly for device support. But what's really specific about Android, it's the userland code, because the utilities, the binary, the libc is completely different from your usual Linux system. Instead of you having GNU utilities, you have custom ones, and you got the bionic libc, which is not the GNU libc. So it makes some pretty big differences. Also, something that is really important is Java. The applications that are written by developers are usually written in Java, but it's not a standard Java virtual machine. Instead, you got the Dalvik virtual machine. I will get back to it afterwards. But also, developers can run and write native code for their applications, and that's using the standard Java interface, that is Java native interface. We'll get back to that later too. And applications, while they can be installed by people by using a USB cable, are mostly distributed via the marketplace or via websites. Concerning hardware, well, mostly ARM CPU, but we can find no applications and Android running on ARM, MIPS CPU, x86, PPC, but the vast majority is ARM CPU. And as outside of phones, it's also used to power TVs, tablet PCs, ebook readers. So you see Android going everywhere. Google is really good at pushing its operating system everywhere. The security model also is very interesting because in contrast to your usual PC, you don't run everything as the same user. Each application runs with its own Unix UID. So applications are separated. One application cannot trace another. And that's really interesting because they added a permission model that is enforced by the Linux kernel that you have to ask for the permission to get location data, to exchange data with other applications. So this model is really interesting. But in fine, everything relies on the Linux kernel for security. If you have a vulnerability in the Linux kernel that allows you to run as the Linux kernel, then everything falls down. And well, the Linux kernel is not really well known for its perfect security record. Then a few words about APK, that is the packages for applications. I'll just say a few words because I'm going to use the terms afterward. So the first thing you can see up there is classes.dex, which contains the main code that runs on the virtual machine. And then you get the manifest, which contains a few metadata, but it's not really interesting. The resources, you get the native libraries you can run, the certificate which signs the application, and the graphical layout. So what's this talk about? Well, you will not see anything groundbreaking, but it's more an overview of what is forensics and what is the current approach for reverse engineering on Android. And so it covers the physical acquisition, memory acquisition and analysis, file system acquisition and analysis, and application reverse engineering. It will not cover more standard tricks like rooting your phone or user data forensics with SMS, emails, because there are already existing tools. Also, jailbreaking and routing is out of the scope. This research was done for the STIC challenge, which is a security conference in France, in French. And so the challenge itself included forensics, reverse engineering, and cryptography. So because I conceived the challenge, I had to do the work before to make sure it was possible to solve it. And there were some really awesome solutions, and I'm quite glad the winner that had the best solution was very kind to translate the solution into English. So you will find the link at the end, but you can get his translation and see what he did. It's really awesome. I encourage you to read it. So, on to forensics. Well, there is something really different from a standard Linux PC, where everything is well known and everything, and you don't have any problem. Android is a very loosely defined platform. That is, Android is just an upstream distribution like the kernel.org is for the Linux kernel, because manufacturers can and do customize Android. They do add patches for the kernel, they customize the applications, customize the GUI and everything. So as they change the code for their hardware, you also find different CPU, GPUs, accessories, devices that are on the phones. So you have to take that into account when you need to do forensics. And evolution is really, really fast because you have had like 5 major releases in 1.5 years. You have to keep up with it. Also, there are really rogue applications that are running on Android. And for example, John Oberheide presented his proof of concept called Rootstrap, which downloaded a series of root exploits from the internet and ran it on the phone, masquerading as a Twilight screensaver or something like that. And you see applications that are leaking information, as we saw with Android. So there is really a need for forensics to be sure if a phone was compromised, you really have to make sure, and you have to check everything. But the first problem is to be able to do forensics is you must be root. And most phones have no root access because, well, to dump the RAM, either you do it with a solder iron or freezing the RAM, I mean, with hardware measures, but it's really complicated. You would like to do it in software because it's easier. So you need to be root to dump the RAM and file systems. Unfortunately, most root exploits, if they exist for your current version, for your phone, usually require a reboot because they're based on the bootloader or vulnerabilities in the flashing method. So you cannot use that, otherwise you would lose the content of memory, which has, well, has many interesting data. So you can try using existing exploit. For example, there is an application called Universal Endroot, which bundles a few root exploits, but it has like 800 kilobytes of code, which you would, well, have to trust before doing a forensics examination. It's not really the kind of code that you would like to run, and it's coming from China. Furthermore, well, Android security model is a bit broken at the moment because carriers lock user out and are slow to push out updates because they don't care if you're out of date. They just want your money. So they still distribute. Yeah. Yeah, you have to, well, when you buy a phone with Android, usually you get a carrier version of Android. They customize it for the guy and everything. But you got no root access, so you cannot choose to install your own Android distribution. And so, since they don't push out updates, usually you are vulnerable to any attacks that has been published. And then they even publish still 1.6 versions, which are not supported by Google in any way, which means you have no security support. So basically, bad guys can root your phones using unpatched vulnerabilities, and if you want to fix your phone, you have to use those vulnerabilities yourself to be able to patch your phone. Unfortunately, the following of the talk assumes that you have root access, because otherwise, well, you cannot do much. You can still desolder the flash to analyze it, but you cannot do anything with the RAM. So concerning memory, the usual way to acquire physical memory on Linux is to, well, get the RAM mapping from /proc/iomem, then just copy the memory using DD from devmem. Well, on x86 it's not really present anymore, and you get that strict devmem, sorry. But on ARM there is no strict devmem, so if there is devmem, you get no problem. And if devmem does not exist, you just load your own module that will recreate it. Unfortunately, devmem, well, is not always present, so you have to find a way to load your kernel module. And kernel modules are really version.config and compiler dependent, mostly because of structures, attributes of sets. So, and in theory, that's easy because since the kernel is published under the GPL, you can get the source from the manufacturer and get the configuration, recompile it, and push it to your phone. Well, in reality, it's not that easy because, as I said, carriers do customize the Android version to everything. So which version do you need? Do you need the manufacturer version? Do you need the carrier version? Did they change anything? Do you get the right version? Because sometimes they push out updates and you only get the source code release afterwards. So you're not even sure you get the right one. And how do you get the .config file to rebuild your kernel or kernel modules? Well, either they activated config gz and then you get it from the phone. Otherwise, well, you hope that it's included in the source code. And in practice, just getting the source code, rebuilding, finding the right configuration, it can take hours for every phone model. So if you pass this way, well, you acquired memory. Now you have to analyze it. On x86, it's pretty well documented, and you just got everything, and even you get software. And most common tasks when you get a physical memory include rebuilding processes to be able to see what was running at that time and what was in their memory, recovering passwords, recovering encryption keys, and everything. You try to identify open files, and you try to identify also open sockets to have an idea of what was the state of the system when it was compromised. The usual way is to, once you have the given kernel version, you can get the attributes of set in the different structures of the Linux kernel. Afterwards, it's pretty easy. Once you have this information, you just look for the PID0 task. That is the first task that is launched at the beginning of the boot process. And it's really easy to find because the command field of the structure contains the word swapper, which is constant. So you have no problem finding it. Afterwards, all processes are linked in a double linked list. So you just walk the linked list of processes, and for each process, you rebuild the virtual address space using the physical memory to virtual address space mapping. And you can also parse VMAs to identifiers and everything. So this is pretty standard. You got no problem doing this on x86. On ARM, it's basically the same. Well, it's based on Linux, so there shouldn't be major differences. But in practice, you have some difficulties that arise. It's first, the RAM itself is not always mapped at address 0. On x86, you just access the RAM beginning at 0 until, well, the end. There, the RAM may be mapped at any address and may be split. That is, there is not a single continuous block of memory to access the physical memory, but you have to be careful of handling the different gaps you could find in there. Also, page offsets, which means the kernel address, well, where the kernel is mapped, sometimes varies, so you have to take that into account too. Fortunately, the k all symbols files seems to always be present, so it kind of facilitates finding the different symbols and structures inside.
And of course, for memory analysis for ARM CPUs, you get no public tools. The only one I know of for x86, well, there are two of them, but for example, volatility, which is one of the most complete solutions to analyze physical memory dump, does support with a few patches x86, but there is nothing for ARM yet. Fortunately, thanks to the stick challenge, some people developed solutions, but they are pretty hacky. So they were made for the challenge. They don't handle the fact that RAM is not always map at 0. Which can be a starting point. Also, there was a few months ago a really interesting research article which is about leveraging the k-mem cache in the kernel. That is, it's used for fixed size allocation of structures in the kernel. And basically, when you allocate something like inodes, inode structure, sockets, the structure size is always the same. So it maintains a cache of recently deallocated data to reuse it as a looker site, basically. And it's really useful because the slab allocator, which is the default on all the phones I have seen, is really good at keeping data after they are not used anymore. So if you can parse the k-mem cache, you're probably going to find a lot of information about dead processes, closed socket, and everything. So this is the standard way of analyzing a Linux kernel. A Linux physical memory dump. But you can do some specific things with Android. One of them is really interesting. It's APKs, that is, the applications packages are just zip files, like a jar file is in Java. So why not carve them out of memory? Because zip is a really interesting file format. It has a lot of redundancy, which means you can leverage this redundancy to extract and recover zip files out of memory. So, as you can see here, you got a end of central directory header at the really end, and where's my pointer? Here, this pointer says, okay, we got n files in this archive, so the data starts here. And afterwards, you get file entries, one for each file, which say, well, the file is at this offset. So if you can find the central directory in memory, you have enough information with all the files to look for the local file headers in memory. And in practice, well, you have to care about fragmentations because, of course, the pages are 4 kilobytes, and a zip file is not going to fit, an application is not going to fit in 4K. So you can try to rebuild the zip file because the zip streams are compressed and the entropy is really high. So you can filter out all the pages which have a low entropy as non-zip data. And once you filter this, you know that you have a local file header and you can have some properties which make it pretty easy to actually rebuild a zip file. And in practice, it works pretty well on small archives, not on bigger archives, because there are an exponential number of combinations of pages once the zip file gets too big. You have too many possibilities to try to rebuild. But the advantage is that it's really easier to implement that full memory analysis because you have no dependency on kernel version, on architecture. It's completely generic. You can use it on any physical memory dump. And on a real-world example, well, that is the stick challenge, it takes a few minutes, like 3 or 4, to fully analyze 100 megabytes memory dump with a Python implementation that is pretty slow. Well, you can also try to dump small DEX files, that is virtual machine code, from memory because they have a magic number. Here you have to be sure that the DEX file is not going to be over 1 page long, otherwise it's too complicated to rebuild. But you'll be able to analyze it afterwards. We will see. So, To sum, we have a memory, we have rebuilt processes, we have information on open files, maybe sockets, but of course we want to see what's on the file system because there are a lot of information on the file system. Of course, to acquire the file system, well, you have to be root as you need the raw access to the memory blocks. You can, as I said, disorder the memory, but it's too complicated. The advantage here is basically you can possibly reboot your phone to get root access because even if you're destroying data in memory, the file system should stay pretty much intact after a reboot. So it should not be destructive and you can probably use it before examination. Afterwards, once you have the root access, you get two main acquisition techniques. The most, in my opinion, interesting one is, of course, of using DD to dump the basic memory block from dev mtd block. Basically, just dump the partitions from the flash. Or you can use a software called Android, which is basically a set of scripts that will dump an image of the file system on the host PC, keeping file permissions, timestamp, and everything. The file system itself on Android is outside. It's yet another file system, flash file system too. It's a log-based file system which was designed explicitly for usage on NAND flash, which is really popular for storage on phones, for example. And well, once you have acquired the physical file system, it's just easy to use IFFS2 utils or IFFS to extract files, like you would do with ChromeFS or SquashFS. One thing that is probably really interesting, I haven't had the time to dig into it, but since yet another flash file system is log-based, it's really designed from the beginning to provide wear leveling, which means it tries not to write data at the same place as it can. So basically, each block is used once you have reached the end of the file system, which means that in theory, deleted data should be still accessible, but I haven't checked if it's exactly the case.
I don't think so. I think these flash file systems, because erasing a block takes that long, they are using a background job usually to erase blocks, so it might not that much.
Well, I've read the specification of the file system, and it could work. It depends really on the implementation, because unless you have the garbage collector running, the blocks shouldn't be erased. So I think it depends on how the file system is tuned. When does it trigger an erase because it's time consuming, and when does it stay as it is? Once you get access to the file data, well, it's pretty easy to analyze. Almost everything is in the /data path. You can get a list of installed package. You can find the Dalvik cache, which contain optimized text files for all the running applications. I will get back on it later. For example, get the checkin.db database that contains a lot of information of connections, when the network is going on, when it's going down. So you can find pretty interesting data in this database. And of course, it contains the application-specific SQLite databases. Each application has the possibility to store data in an application-specific database, which is really easy to dump using SQLite afterwards. And the applications themselves are installed in /data/app. And of course, if you find something that is really weird there, well, you will have to reverse it to find what's going on. And reverse engineering of, well, Android applications is a new word in itself. Also, well, Android is based, Android applications are programmed in Java. As I said, the Dalvik virtual machine is not a standard Java virtual machine. And actually, the code is compiled to Java bytecode, but there is a tool afterwards that converts this bytecode into the Dalvik opcodes. And everything is merged in a file called classes.dex. In essence, the virtual machine is register-based instead of stack-based, which is a major difference. But as I said already, native code, that is code, for example, code in C, in C++ to access lower level functions and have better performance is still accessible with the Java native interface. And the native code is stored in shell library, .iso in the APK, and you can find resources with images, interface data, you can find anything. And interesting also is the manifest and signature, because app signing is mandatory, so you're sure if an application is installed that there was someone with a certificate that signed this application. Unfortunately, you cannot enforce a certain certificate authority to allow installation. Every self-signed certificate is always going to be accepted. You have to patch the system to restrict that. Just going to show you a little example. So this is just a standard RC4 cipher code that written in Java. Just the get byte function from RC4, and we're going to see how it's done in practice. There is nothing much particular here, just attributes access in local variables, and that's it. So the first tool that you will find is TextAmp, which is in the Android SDK. It's really a basic disassembler, like you would say objdump for native code. And as you can see, it's pretty verbose. In particular, you can find that you can still see the method signature. You have the whole class path, the class itself, the method. And here you can see that it returns a byte. Here you can see that you have an attribute access, which is x, the standard state variable. Nothing really special here, except that it's not that easy to read. Fortunately, there are other tools. TextAmp is really the most basic one that you can try to use to debug simple things. But if you want to really reverse applications, you will have to resort to other tools. For example, there is a tool called Backsmally and Smally. It's a disassembler and assembler that is way easier to use than Xdump, because, well, the code is way cleaner, it's indented, and you get references. So it's basically the same code, but with a better presentation. And which is really interesting is that you can modify that code and recompile it afterwards. So modifying Android applications is really easy. And since any certificate is accepted, you can just modify the code, resign it with your self-signed certificate, and reinstall it on the Android. Of course, it's used by many people to crack applications. And you can you can run it on APKs directly. It will rebuild the directory structure, and to modify it's really easy. And you could use Android APK tool, which basically is Smally, Backsmally, plus a resource decoder, because, for example, the layout, the graphical interface is not is defined in XML on your SDK, but it's afterward compressed and encoded before being put on the phone. So it basically decodes it and allows you to modify the interface directly. And it allows for Smally code debugging, integrates with Eclipse, and you can just trace code running on your phone in assembly. So that's pretty useful. And the next step after disassembly is the compilation. Of course, in Java, it has been done since years, but here the virtual machine is different, so it's not that easy. You got two main tools that are used to convert the DEX code from the Dalvik virtual machine back to the standard Java bytecode. So the first one was NDX. It was presented 2 years ago, I think.
It's really interesting, but it was more a proof of concept, and unfortunately, it fails often. So, and the resulting code is not that readable. There is a recent fork that may work better. They mainly include bug fixes, but well, there is another one that was developed by the Chinese developer, which is completely documented in Chinese, so you basically have to reverse the decompiler to understand how it works. But it works quite well. It generates a jar file that you can decompile afterwards to this JDGI, for example, or JEB. And it's really, really working well. You can basically throw any application at it, and it will basically work. And just an example of the RC4 function you had before. It's the result of the decompilation with Java decompiler of the dex2jar output. So even if you lose a bit of information, it's pretty reliable and useful. There is another thing that you can encounter. It's ODEX. It's optimized DEX. That is, DEX files are really generic and they are not, well, really good for performance. So when you're installing an application on an Android phone, it will take out the classes.dex file, optimize it, and store it in the Dalvik cache folder. And it applies platform-specific optimization, like using specific bytecodes, using vtables for methods, offsets for attributes, method inlining for small functions. So the code is way harder to read. But if you try to recover DEX files from memory directly, or if you find some traces in Dalvik cache of an application that is not here anymore, you will have to reverse it. And as you can see, this small example shows that attribute access is, well, you can see the object plus C. So you have completely lose the attribute name. It is the same for methods. You only have a reference to a vtable. So the code is really hard to read, and you would have to do a manual lookup every time to find attributes and method. Fortunately, Baxmol handles DEX files, ODEX files, with an operation called dodex. Unfortunately, to resolve all the structures offsets and the methods offsets, it needs all the dependencies. It means if you find the ODEX file, you really have to have all the libraries needed to run the application itself to be able to deodex it. The last specific part of reversing Android applications, which fortunately doesn't appear that often, is GNI. And so it's the native code running part of an application. And so at the beginning, when you load the application, the shared library that is in the archive is loaded. And afterwards, the methods that are present are used directly by Java code. And those methods themselves can exchange information with Java, call methods and everything. And they use a structure called GNI environment to interface with the main Java code. And otherwise, it's just syscall libraries. You can do everything native code can do. But the specificities of the environment, GNI environment, can be used to ease reversing compared to standard C code. Because you have this specific variable, you can load the structure definition in IDE to, if you assign it onto the right variable, you will see function calls directly. And you can do the same in Xrays. For example, in this screenshot, you can see in the first part, well, you got nothing really interesting. At the end, the last line, BLX R3, is a function call. But if you assign the GNI env type to a good variable, you will see that you can resolve the call to get string UTF cards. And at the end, in the third part, you can see easily that this part just gets a Java string and recovers the UTF cards to handle it. With Xrays, it's basically the same. You just apply the definition,
And at the end, you see that it's called set byte-array region, and you got some pretty readable C code instead of hard to read spaghetti assembly. And in this part, the assembly itself is not classic ARM code. It's in thumb mode, that is the small 16 bits mode of ARM, which is a bit more annoying to reverse. So in the future, unfortunately, we still need complete and particularly reliable tools for memory analysis, because right now we are kind of short of tools. And for file system analysis, you only have tools to unpack the file system, but you don't have undelayed capacities, you don't have well, advanced analysis to recover information. And unfortunately, Android is moving forward really, really rapidly, so you have to adapt as well with the evolutions of the operating system itself. For example, 2.2 introduced just-in-time compilation, and is it a big deal? I don't know, I haven't looked into it yet, but probably optimized DEX files are gone, so you probably won't be able to use them to reverse and uncover rogue applications. Also, some phones, most notably those using ST microprocessors, can use virtualization, and some phones actually use that to run 2 operating systems in parallel. So if you dump the virtual memory, you really have to be careful, because the physical memory can be used by either operating system. So right now, I only know 1 phone using this CPU, but in the future, maybe more are going to do that. You're going to see. And of course, you will be where I just talked about ARM, but you will have to handle MIPS, PPC, and everything, because, well, the diversity of Android devices is going to explode in next years. Well, you can find a few references here. They can be useful if you want to dig into reversing or forensics for Android. And I thank you for your attention. If you have any question, please do.